Hello everyone, I am Rio and Abonita from Visit Science 3A. For today's lesson, I will discuss about lifting mechanism, atmospheric stability, and how stability changes under the moisture and atmospheric stability. We all know that moisture in the atmosphere is an important component in understanding our atmosphere, as it allows us to understand the concept of how air can flow and be lifted through four main processes known as lifting mechanism. Consequently, atmospheric stability helps us to understand whether a parcel of air would sink, rise, or remain stationary, and thus determine whether clouds form or not. Believe it or not, air is actually a fluid. This is because a fluid is any substance that flows and has an indeterminate shape. But this is different from a liquid, which is a specific phase of matter. All liquids are fluids, but not all fluids are liquids because gases are also fluids. So, air, which is a mixture of various molecules in their gaseous phase, definitely flows. Like wind, air flowing around horizontally, but air also flows vertically, which we call lift. Meteorologists use a construct called an air parcel to help them describe the processes associated with air in motion. An air parcel refers to a small volume of air large enough to contain a great number of molecules but small enough so that energy and mass are nearly constant within its boundaries. Air doesn't live all by itself. It needs help. But what processes lift air? So there are four main processes that lift air, known as lifting mechanism. These are orographic lifting, frontal wedging, convergence, and convective lifting. When air does flow upward, we get some interesting weather process like cloud formations, precipitation, thunderstorm, tornadoes, and hurricanes. Let's explore these processes and know how they contribute to observable weather patterns. The first way that air is lifted is through orographic lifting. This is when air is lifted over an obstacle, like a mountain. As air moves across an area, it sometimes run into obstacles like mountains, and of course, it has nowhere to go but up. As the air is forced up, the side of the mountain cools and condenses, which means it gets more compact. Most of the moisture in the air gets forced out as the air condenses, which forms a cloud over the side of the mountain, shown below, known as the windward side. It is called the windward side because this is the side of the mountain that wind first encounter. The cloud is full of moisture, so it's also pretty rainy on the windward side. Once the air goes over the top of the mountain, it sinks back down again, and as it sinks, it warms up. However, it left most of its moisture on the windward side. So this air flowing down the backside of the mountain, also known as the leeward side, is not only warm but very dry. Another way that air is lifted is through frontal lifting. A front is where two different air masses meet. So, frontal lifting is when one air mass along a front gets lifted or lifted up over the other. A cold front occurs when a cold air mass advances onto a warm air mass. A warm front is the opposite when a warm air mass advances onto a cold air mass. A cold front is like jumping into a lake in the middle of winter. Your body is quickly shocked by the change in temperature, and the warm air experiences something similar and it's quickly and forcefully pushed upward. And because of this, we get clouds forming quickly as well, and they form vertically instead of horizontally. And this make the best thunderstorm clouds. So cold fronts tend to bring dramatic changes in weather too. But Warm air along a warm front is quite different. It gets slowly lifted up instead of dramatic lift we see with cold fronts. It's more like getting into a hot tub, slowly stepping in and letting your body adjust to change in temperature. Since air is lifted so slowly along a warm front, cloud formation is more horizontal than vertical. This means that while the weather does change, it's much less dramatic than with a cold front, and you'll likely experience mild rain over a wide area. Next, we have convergence, which is when air converges in the center of a low pressure area as air flows horizontally and meets along the surface of Earth. It's forced upward since that's the only place it can go. And convergence is responsible for some well-known weather events like hurricanes and cyclones. And in fact, these storms only survive if wet air continues to converge in the center, and if it stops, they die out. The eye of a hurricane is the low pressure center where the air comes together, and as the air rises, it brings up moisture from the ocean it formed over. This is also why a hurricane can form over land. The wet air converges and rises up through the low pressure center, and as you know now, it cools and condenses as it is lifted up. Condensation releases a lot of energy, and this is the very energy that drives the storm along its path. As long as there is moist air being drawn up into the eye, the storm continues to soldier on. Certain areas absorb more heat during daylight hours and will cause the atmosphere above to become warm. This warm air will rise and create thermals. Birds often use thermals to their advantage to reach great heights. Finally, if one surface is heated more than its surroundings, it will be buoyant and will rise in thermals. This localized convective lift may produce summer thunderstorms, but the lift usually isn't strong enough to produce deep clouds. So, the atmospheric stability refers to a condition of equilibrium. It is the air's tendency to either rise and create storms, or instability, or to resist vertical movement, or the stability. The simplest way to understand how stability works is to imagine a parcel of air having a thin, flexible cover that allows it to expand but prevents the air inside from mixing with the surrounding air. Like of a party balloon, and imagine that we take the balloon and force it up into the atmosphere. Since air pressure decreases with altitude, the balloon will relax and expand, and its temperature will therefore decreases. If the parcel were cooler than the surrounding air, it would be heavier since cool air is denser than warm air, and if allowed to do so, it would sink back down to the ground, and the air of this type is said to be stable. On the other hand, if we lifted our imaginary balloon and the air within it was warmer, less dense than its surrounding air, it would continue to rise until it reached a point where its temperature and that of its surrounding were equal, and this type of air is classified as unstable. But meteorologists don't have to watch a balloon's behavior every time they want to know atmospheric stability. They can arrive at the same answer simply by measuring the actual air temperature at various heights, and this measure is called the environmental lapse rate. So for the key terms, stable air, the parcel moves back, and in the stable air, the parcel moves away from the original position, and the environmental lapse rate is the actual temperature of the atmosphere. In the absolute stability, the environmental lapse rate is less than the adiabatic rate, and the rising air continues to cool any layer in the atmosphere where the rate of actual temperature decrease or increase. with height is less than the cooling rate of the moist adiabatic lapse rate. And the most stable layers are inversions, where temperature increases with height. In absolute instability, the environmental lapse rate is greater than the adiabatic rate. Any layer in the atmosphere where the rate of actual temperature decrease with height is greater than 9.8 rapid cooling with height. These are termed superadiabatic lapse rate. They most commonly occur at the surface during strong solar surface heating. Conditional instability is the most common type of atmospheric instability. This situation prevails when most air has an environmental lapse rate between the dry and wet adiabatic rates. The air is unstable if saturated but stable if unsaturated. Saturated air cools less with height due to latent heat release and thus allowing the parcel to be warmer than the environment if lifting occurs in a conditionally unstable environment. So, how stability changes? There are factors that enhance instability. First is intense solar heating that warms the lowermost layer of the atmosphere. Next is heating of an air mass from below as it passes over a warm surface. And general upward movement of air can cause by any of the lifting processes. And last, radiation cooling from cloud tops. So the factors that enhance stability is the radiative cooling of Earth's surface after sunset. Next is cooling of an air mass from below as it passes over a cold surface. Next is general subsidence within an air column.